Previously, we have studied induction transformer and DC machine, where we have used starter for DC machine, but we don't use starter for transformer because transformer is a static device and it is purely electrical device and no rotating part in the transformer. That's why we all know the electrical time constant is very less than the mechanical time constant. So the back EMF generator to generate back EMF in transformer, it takes very less amount of time for, but for motor, DC motor or induction motor, it takes time to generate back EMF because we know the back EMF depends on the speed of the motor. For the, that's why to get the steady state speed, it takes some time, and to generate the back EMF, it takes much time, and that time the starting current of the motor is very dangerously high. That's why we have to use starter that so that we can minimize the starting current. For induction motor, we can see the starting current is the 4 to 10 times of the full load current of the machine. So, method to start the induction motor so that we can maintain the starting current in normal range. We know already we have studied the two types of induction motor is there. One is slip ring induction motor and other is cage induction motor. Slip ring induction motor has special provision that we can connect external resistance to the rotor so that we can maintain the starting current. But for cage induction motor, there is no provision so that we can connect external resistance to the rotor so that we can maintain the starting current. For cage induction motor, there is some methodology that we can use to maintain the starting current. First, we will discuss direct online starting, then we will discuss stator resistance starting, then auto transformer starting, and then starting. Let us discuss direct online starting. Direct online starting means we will start the motor at full voltage. So there is a question arise that if full voltage is applied, then starting current may be 4 to 10 times of the full load current. But this methodology is applicable for low wattage motor. Here we can see that this direct online starting can be done for low wattage motor up to 7.5 kV. If the starting current of if the rating of the motor is very high, then starting current would be very high. If starting current would be very high, then it will affect the other consumer from where they are supplying the power. We are taking the power. If high current is drawn from the supply, then voltage may dip or it will affect the other consumer. So this methodology is applicable for low wattage motor, so that for low wattage motor it will reach the steady state speed at very short time, so that back EMF will be generated at very less time. So starting current will be reduced very fastly, so that direct online starting methodology can be used. Now we can see a direct online starting method. The full voltage is applied to the stator. Now, if the stator is delta connected, so for delta connected motor, the line voltage equal to phase voltage. So phase current, we all know per phase current with I2 of the rotor, then the total power of the at the starting will be 3 I2 square R2 by S. At starting condition, the S slip value is 1. So this value is the total power, and the torque will be the power by the synchronous speed of the induction motor. From that, we can see the torque of the starting torque or full load torque. Any torque is current square of this proportional to the square of the current. Now for starting current, this is the for direct online starting. starting current. This is the torque current relationship. The torque is proportional to the square of the rotor circuit current. Now for starting condition, the speed is equal to 1 because the at starting condition the rotor speed is 0. Okay, so we have to remember the direct online starting can be used only for the low wattage or low rating induction motor. Now, next methodology is stator resistance setting. In this stator resistance setting, how we can minimize the starting current? We will connect a resistance between the motor and the supply. If a resistance of series resistance is connected each phase of the supply between the motor, then there is a voltage drop across the resistance, so full voltage will not be appeared across the induction motor. So less voltage, suppose x time voltage after using this resistance, x time voltage is of the full load supply voltage is appear across the motor. So there we can see the current drawn from the rotor circuit, voltage will be also x time, so current also will be x time. This x value is vary between 0 to 1, so we can see starting current will also reduce. Now we have already studied the torque of the at this condition is dependent the I square of this current square of the value. So starting torque will be, we can see the starting torque between and full load torque at starting condition, the slip equal to 1, so I square by s, and full load torque I at full load square by s. This s in the upper side at starting condition s value is 1, so full load torque and starting torque relationship is this. So using this resistor stator condition, we can see that starting current is reduced by x time of the direct online starting. So and the starting torque will be x square time of the direct online starting torque. Okay, so x will be, we have to remember x will be varied between 0 to 1. Now third condition is auto transformer starting. Now we have to discuss one more thing, that the starting stator resistance starting, we will generally use stator reactor starting, because if we use stator resistance starting, then unnecessary power loss will be there, I square R will be there, which is not desirable. So if we use a reactor, then unnecessary power loss will not happen. So we'll usually use stator reactor in this resistance part. We can use also resistance also. Now auto transformer starting, we will use a auto transformer between supply and the motor. Now the starting current is always is the current which is drawn from the supply. Okay. Now if we use a three-phase auto transformer, which is turns ratio is x, now the current in the secondary of the stator auto transformer is connected with the motor. Now if the turns ratio is x, then the secondary output voltage will be the x time of the per phase voltage x. So or here use is k. So k time turns ratio is k, so k time is v by root 3. So if the voltage across this is reduced by k time, then current also will be reduced by k time in the secondary. But in the primary condition, the current will reduce by k square time, because if we apply the transformer ratio in the transformer, we know transformer primary current into the N1 equal to secondary current into N2, then we can see that transformer starting current will be k square time of the DOL starting current. And we can, from the derivation, we can also see the starting current is always depend, the torque is depend on the rotor circuit current. Rotor circuit short circuit current is k time of the DOL starting. So the torque is reduced by k square time, but current is also reduced by k square time, because start when we'll considering starting current, that is the supply current. So using the transformer principle, we can see the starting current will be reduced by k square time of the primary of the dual starting. So this is a very useful method. Here is starting current and full load starting torque and full load torque is relation is given by, and the k is vary 0 to 1. So using this, the torque will be very starting torque will be decreased by k square time. Also starting current also decreased by k square time. But in the we have to analyze that in the stator resistance starting, we have seen that the current is reduced by x time into dual starting. But in the auto transformer starting, it is k square time, and k will be vary also between 0 to 1. So starting current in the auto transformer starting will be more or less than the stator resistance starting. And now the last topic we will discuss, which is the most important topic, that is start delta starting. Start delta starting, we will not use any auto transformer or starter resistance. For start delta starting, we can use for those motors which will be normally delta connected motor. At the starting condition, it will operated as star connection, and when it is running condition, it will operated as a delta. Now, in the laboratory, you can see that six terminal of the will be there when it will be acted as a when the motor is started, then it will operated in star connected, and when it is in running condition, then it will operated as a delta connected motor. If we delta to star, if we connect, then we know that starting voltage per phase delta voltage is line voltage by root 3 times. Okay, so phase voltage will decrease by root 3 times. So if phase voltage is decreased, then phase current will also decrease by V phase by root 3. Means if delta connected motor, per phase current is V by resistance. Here per phase current is V by root 3 by resistance. So per phase current is divided by root 3, and here for star connection, line current and phase current are same, but for delta connection, line current would be root 3 times of the phase current. So total current is reduced by 1 by 3 times, because here we are considering phase current and line current same. So phase current is I. For star connected phase current is I by root 3. And delta connection line current is root 3 into I. And here we are getting line current also I by root 3. So if we divide it by this root 3 by I and I by root 3, we can get at the starting we get 1 by 3 times of the starting current of delta connected motor. So using charge delta starting, we can reduce the current by 1 by 3 times. And using we all know the torque is dependent on the current square. Now here we can see the starting current is per phase current is 1 by root 3 times. So if we derive, then we can see the torque ratio of direct online starting and start delta starting. Torque will be also 1 by root 3 times of the full load torque. Okay, so for start delta starting and auto transformer starting, we have seen that the starting torque is also reduced by square of the root 3 for auto transformer starting, and for start delta starting, and for auto transformer starting, the starting torque is reduced by 1 by k square time. But and also the current for both cases is reduced by for start delta starting with 1 by 3 times, and for the auto transformer starting we can see the current is reduced by k square time. Okay, so from this methodology we can see that at the starting position we can reduce the starting current by applying this method, and the most efficient method is transformer starting and start delta starting. This methodology is maximum we will be using in practical conditions. Now, one thing here we have to discuss. Previously, we said that slip ring induction motor has special provision. We can use the rotor circuit resistance across the rotor. If we use the rotor circuit resistance across the rotor in the slip ring, then we can if resistance in the rotor circuit is increased, so rotor current and the reflected current in the primary also is reduced. This is the very important provision which is only applicable in slip-ring induction motor. So for cage induction motor, we will be using start delta or auto transformer starting, stator voltage starting. This is the starter of starting of three-phase induction motor.